Today we will look at how moles works in solutions, or to say in a fancy chemistry way, molar concentration. So in this video we're going to be looking at the concentration equation, making a standard solution, titration followed by back titration. So the key thing to understanding concentration is remembering the unit for volume. So the unit for volume is decimeters cubed, and 1 decimeter cubed is the same as 1 litre, but we don't use litres, we use decimeters cubed. Easy. Then to convert between decimeters cubed and centimeters cubed, you need to divide by 1,000. As the equation that we're going to be looking at in a bit only works in decimeters cubed, as the concentration, as the unit for concentration is moles per decimeter cubed. So first of all, we're going to be looking at an example using sodium chloride. So this is the equation that we've looked at in a previous video. So we're going to measure out 1 mole of sodium chloride. So 1 mole of sodium chloride would have a mass of 58.44 grams. And if we put that 1 mole of sodium chloride into a 1 litre of water, we would have a concentration of 1 mole per decimeter. Here's another way of writing it. The shorthand is in square brackets. So whenever you see square brackets in chemistry, it could mean concentration like this, or it could mean that something has a charge. So it's representing an ion. But to figure out the difference between the two, is very easy. Back to solutions, it's going to be very rare that we're going to have 1 litre of a 1 mole solution. So your 1 mole per decimeter is a great concentration. However, you might not always need a litre of it. So we're going to use this handy equation here. So this equation triangle here is the link between concentration, concentration in moles per decimeter cubed, volume, which is in decimeters cubed, and then moles, which has the unit mole. So if we wanted to find out how many moles of sodium chloride would be in 50 centimeters cubed of a 0.1 mole per decimeter solution, we can find that out to be 0.005 moles. So using the equation here. So if we want to find out moles, it is concentration times the volume. And remembering, we need to divide centimeters cubed by 1,000 to get our answer into decimeters cubed, and then here is our answer. Okay, so now on to our first practical use of using the concentration equation triangle. So it's making a standard solution. So making a standard solution is explicitly mentioned in your syllabus, so make sure you learn these steps. So in our example, we're going to be making a copper sulfate solution because it has a nice lovely blue color, and we want our solution to have a concentration of 0.5 moles per decimeter cubed, and we want to have a litre of that solution. So the first thing we need to do is figure out how many moles are needed to make this solution, because we know the concentration, we know the volume, but we don't know the number of moles. So we're using this equation here. So concentration times volume will give us the number of moles that we need. So in this case it is 0.5 moles. Happy days. But we don't have a moles balance. We can't just measure out moles directly. So we need to use the equation triangle from a previous video, which links moles to mass. So we know the moles we need. We can calculate the molecular mass of copper sulfate, which is this number here. And then multiplying that by 0.5 is going to give us our mass. So half a mole of copper sulfate crystals is going to have a mass of 78.8 grams. So look at that, as if by magic, we've already got our 78.8 grams of the copper sulfate way down. So again, because you want a standard solution, you want to have this to have a high degree of accuracy. So using the 2 decimal place balance. Then we are going to transfer this to a beaker. And whenever we're doing any of the transferring of anything throughout this method, you're always going to be using distilled water, so that's really important. So distilled water only contains water, no other salts or minerals. So we've transferred it from our weighing boat to a beaker. we've dissolved it, so we're using a stirring rod to dissolve our crystals. Then we are carefully pouring our copper sulfate solution into our volumetric flask. So the volumetric flask is the same size as the solution you want to make. So in this case, our volumetric flask is going to be 1 decimeter cubed in size. So we're transferring everything from the beaker into the volumetric flask. Then we're going to be rinsing out the beaker with distilled water again, and this is just to make sure every little bit of copper sulfate from the beaker ends up in the volumetric flask. Then, once the beaker has been washed, we're then going to be washing the funnel. So washing the funnel with the distilled water. Then you're going to fill up your volumetric flask with distilled water until you get very close to the line that indicates 1 decimeter cubed. So volumetric flasks are great because they're very accurate, but they only measure 1 volume. So you're going to be very carefully distilled water to just below the line. Then you're going to very slowly, drop by drop, add distilled water until your meniscus is just above the line, as you should hopefully know from using measuring cylinder. Then once you've added the correct volume of water, distilled water, you're going to put a stopper on your volumetric flask, and then you're going to thoroughly mix it. So I've got my imaginary volumetric flask here. So you invert it, swizzle it, back down, invert, swizzle it, back down, and you do that about 10 times, and now you 100% know that you have a fully mixed equal concentration of, in our case, 0.5 moles per decimeter of copper sulfate. Happy days. Now you're ready to use your solution. Okay, so now on to another great thing you can do with solution calculations, and that is to find out the concentration of an unknown solution using a method called titration. So let's go through the steps of titration now. So first things first, you're going to measure out 25 centimeters cubed of a solution with an unknown concentration. So just like the volumetric flask, we have our volumetric pipette, and these are very good at measuring out volumes very accurately. So your unknown solution is getting measured out using the pipette, and then that is going to go into a conical flask. Then you're going to fill a burette. So this is the burette. So you're going to fill the burette with a solution of a known concentration. So you fill that all the way up. If you do it properly, you wash it, clean it, wash it again, fill it up, and then it is filled with your solution of a known concentration. Then titrate until the endpoint. So that just means adding what's in the burette into what's in the conical flask. And then you're going to keep doing this until you get an endpoint. So this is usually going to be a color change of some kind. Then you're going to record what's called the titer value, and then once you've got the titer value, you can do quite a few calculations, and then you can calculate the concentration of your unknown solution. So let's look at an example. So a classic titration is an acid-base titration. So in our case, we've got some hydrochloric acid, but we don't know its concentration. The label's fallen off, can you believe it? So we're going to measure out 25 centimeters cubed of our acid. We don't know what the concentration is. We are then filling our burette with a known concentration of sodium hydroxide. So sodium hydroxide reacts with hydrochloric acid. So the sodium hydroxide is going to be filling our burette all the way up to the top. Then you do this quite a few times, and then this will be your average titer value. So you do it once, and that's just called the rough titration. Then you do it at least 3 more times to then give you your average. But ideally you do it at least 5 times, and if you're doing this for an IA, you're going to do it at least 10 times. So I've got my average titer value. So using our equation triangle from before, we can figure out the moles of sodium hydroxide, because it's the concentration times the volume. We know the concentration, and then through the experiment we've figured out the volume. So yeah, 0.1 is the concentration, and then yeah, the volume 10.4, and then again you're divided by 1,000 to get it into decimeters cubed. And now we have the number of moles. So here's the really exciting part. So using our balanced equation, we know the ratio between sodium hydroxide and hydrochloric acid. So because we've got 1.04 times 10 to the negative 3 moles of sodium hydroxide, that's going to be the same as the moles of hydrochloric acid. Happy days. So now, yeah, using our equation triangle again, this time we're solving for concentration. So we've figured out our moles, we know the volume because that's 25, we put it into our equation, and then we get our concentration of acid. There we go, it's as simple as that. Happy days. Okay, so now on to the final thing today that we're going to be looking at with solution. So we can do a different type of titration, and this is called a back titration, so a back titration. So you use this method if the acid or base in the burette can't react directly with what is in the conical flask. So if we go back to this example, so here the sodium hydroxide can react immediately and directly with the hydrochloric acid. So as soon as it gets added, the reaction happens. But this is not the case with all types of titration. So this is when, yeah, we use the back titration. So an example when you would use a back titration is if you wanted to find out, yeah, how much calcium carbonate is in an eggshell, or yeah, how much base is in an antacid tablet. So in both of these cases, if we just did these two steps over here, the eggshell can't react directly with, in this case, the acid that's going to be in the burette. So what you do is you do a reaction earlier, and then doing a bit of sums, you can figure out, yeah, in this case, how much calcium carbonate is in your eggshell. So yeah, both of these, so yeah, the antacid in the eggshell is a great experiment that you can do in your IA. So there you go, that's an IA idea for you if you're running short of them. But yeah, so let's look in more detail about how this method works. So yeah, we've got our 4 steps, and I must say this diagram is not to scale. Yeah, we've got our 4 steps, so let's see what's going on. So first step, yeah, make your standard solution. So you need to make your standard solution. So you can decide how much you want of your standard solution, but the key thing is, with your standard solution, you're going to know exactly how many moles are in your standard solution. So then when it gets on to step 2, again, you're going to know exactly how many moles are in the 25 centimeters cubed. That's really important when we get onto the calculations. Then your third step is add a known mass of your sample. So in this case, we're going to be using an eggshell. So you're going to know how much eggshell is going into your conical flask. Then these steps are going to be similar to before. So yeah, complete the titration until the endpoint. So in this case, yeah, we're going to have sodium hydroxide again is going to be in here, and the sodium hydroxide is going to be reacting with the hydrochloric acid. Whatever hydrochloric acid is has not reacted with the eggshell. And then, yeah, the final step, calculate the number of moles in your sample. So this will probably make a bit more sense once we've looked at a real life example. So yeah, in our first step, make your standard solution. So our standard solution is going to be hydrochloric acid with the concentration of 1 mole per decimeter. So remembering this is a shorthand way of writing that. Then pipette out 25 centimeters cubed. So in our 25 centimeters cubed sample, we've looked at this calculation already, so I'm not going to go through it in a huge amount of detail. But yes, we know how many moles are in our 25 centimeters cubed. So this is the really key part. Then, in our example, we're going to be measuring out our eggshell. So yeah, so in method you could aim, so like I want to weigh out 1 gram of eggshell. It doesn't matter if you get exactly 1 gram, but the key thing is, yeah, that you record your answer to exactly what you've got. So yeah, 1.07 grams of eggshell. Then, yeah, the eggshell, so the calcium carbonate in the eggshell is going to be reacting with the acid. So it's going to be reacting with your 0.025 moles of acid. Now, the point of the titration is to find out how much acid is left over. So this is going to be in excess So we're going to have more acid compared to the calcium carbonate in the eggshell. We don't know how much calcium carbonate is in the eggshell, but we know how much acid is going to be left over from our original 0.025 moles from doing the titration. So this is what the point of the titration is same as before, using the sodium hydroxide, we can now find out how much acid we have, because that becomes an unknown amount. So we've done our titration lots and lots of times. So again, this is our average titer value. This time we've got 26.2 centimeters cubed. So finding out the number of moles again using this equation. So now we know how many moles of sodium hydroxide we have. So this is how many moles of unreacted acid we had in our original 25 centimeter cube sample. So we know we had this many moles at the start, but we're now going to minus the moles that reacted with the sodium hydroxide in the titration. So now we know the exact number of moles that reacted with the eggshell. So that's the really key point here. So now we know how much acid reacted with the eggshell. So we've got our equation here. So in this case, the hydrochloric acid to calcium carbonate is in a 2:1 ratio. So once we know the moles of the acid, we divide that by 2, and then we get the moles of calcium carbonate. Now we know the moles of calcium carbonate, we can convert it to a mass, back to a mass, again using this equation that we've already looked at. So we know we've got 0.99 grams of calcium carbonate in our original 1.07 grams of eggshell. Converting that to a percentage, and we get 92.3%, which is vaguely what we would expect. So it's around 95% calcium carbonate should be in egg cell. So happy days. So there we go. So that is an example of a back titration, and you can use that for your IA if you want. And it's a really lovely experiment to do as well. As always, thank you for watching. And please remember to tell your chemistry class about these videos and to like and subscribe if you want more IB chemistry content. Ciao.